In this chapter, we're going to explore the disciplined world of software quality assurance. We're going to look at how we find and fix problems before they ever affect a user. It's all about making sure the software we build is solid and reliable.
All right, so here's the plan. First, we'll get the language straight. Then, we'll jump into the detective's toolkit, the core testing strategies. We'll talk about how to test smart, not just hard, and look at the usual suspects when it comes to bugs. From there, we'll broaden our investigation to inspections and big systems, and wrap it all up with what it all means.
Okay, first things first. Before we can even start hunting for problems, we've got to make sure we're all speaking the same language. You know how we toss around words like bug, error, or failure all the time? Well, in software engineering, those words have very specific meanings, and getting them right is super important.
So why does good software go bad? You'd be surprised. It almost always starts with something small, a simple human slip-up. But that one tiny mistake, it can create ripples that spread through the whole system, and suddenly you've got a huge problem on your hands.
Let's start with a failure. This is the part that everyone sees, especially the user. It's the moment the software doesn't do what it's supposed to do. It could be a full-on crash, sure, but it can also be more sneaky, like a wrong number in a report, the app freezing for a few seconds, or even just really unhelpful help text. Basically, if it breaks a promise made in the requirements, it's a failure.
Okay, so that's the failure. But what causes it? Well, that's what we call a defect. Think of it this way. The failure is the symptom, like a cough. The defect is the actual illness causing the cough. It's the flaw hiding in the code, or the design, or heck, even in the original requirements. This is what most people call a fault, or, you guessed it, a bug. And if we keep digging, where did that defect, that bug, come from? It all comes back to a human error. An error is just a mistake a person made. A developer typed something wrong. A designer misunderstood a requirement. It's that initial slip-up that plants the seed for a defect, which can later bloom into a full-blown failure. So you can see why this quote is so perfect. Testing really is like detective work. You can't just randomly look for clues. You have to get inside the heads of the programmers, the designers, and even the end users. You have to think about how they think, what mistakes they might make, so you know exactly where to look for those hidden defects.
All right, we've got our terminology straight. Now, let's open up the detective's toolkit. Every good detective has their methods, right? For us, the two most basic tools in our kit are black box and glass box testing.
So what's the difference? With black box testing, you're on the outside looking in. You treat the software like a black box. You can put stuff in and see what comes out, but you have absolutely no idea what's happening on the inside. Glass box testing is the total opposite. It's like the box is made of glass. You can see everything, the internal code, the data structures, the whole shebang, and you use that inside knowledge to guide your tests. Now, glass box testing can get really systematic. You can actually map out the code's logic, kind of like a flowchart. The big goal here is something called edge coverage. All that means is you want to create tests that force the code to go down every single possible path, every if and else branch. Yeah, it's way more thorough, but it definitely takes more time. That's why we usually save it for the really critical parts of the system, the stuff that absolutely cannot fail. Okay, so a detective isn't going to interview every person in an entire city, right? That would be crazy. It's the same for us. We can't test every single possible input. We need a smarter way to investigate, a way to narrow down the field. Just think about it. Imagine you have a simple function that just takes an integer. A standard integer can have over 4 billion possible values. Are you really going to test all of them? No way. It would take forever. And for what? If the code breaks for the number 50, it's probably going to break for 51 too. It's just not a good use of time.
And this is where the smarts come in. The solution is something called equivalence classes. It's a fancy name for a simple idea. We group inputs together that the program should handle the same way. So, for a simple month validator, you don't have billions of inputs. You really only have 3 groups, right? Invalid numbers that are too small, like 0 or less, valid numbers from 1 to 12, and invalid numbers that are too big, like 13 and up. You just test one number from each group and you're good to go.
Now, here's the real pro tip. The most interesting stuff happens right at the edges, the boundaries of these classes. So for our month example, you absolutely want to test 0 and 1, and then 12 and 13. Why? Because that's where programmers often make mistakes. Those tricky off by 1 errors, they live right on these boundaries. Experienced detectives know that criminals tend to have patterns, an MO, right? Well, it turns out software bugs do too. If you know the common patterns, you know what to look for, and that makes you a much, much better detective. So, here's our rogues gallery, the usual suspects of the bug world. You've got your basic stuff, like incorrect if statements, or those classic off-by-one errors where a loop runs one too many or one too few times. But then you get into the more complex criminals, like timing issues in multi-threaded code that can cause a total deadlock, or those sneaky memory leaks that slowly eat up resources until the whole system grinds to a halt.
Whoa, take a look at this line of code. This is supposed to decide when to sound a landing gear alarm. Now, just trying to read that and figure out if it's correct, it's a nightmare, right? This is a prime hiding spot for a really dangerous bug. You can't just eyeball this. This is exactly why you need a systematic approach using those equivalence classes and boundary tests for every single variable in there.
Up to now, everything we've talked about involves running the code to see if it breaks. But what if I told you that's not the only way to find bugs? Sometimes the smartest move is to put the code under a microscope and just read it. Examine the evidence directly.
And that brings us to inspections. Think of it this way. Testing is a dynamic activity. You have to execute the code. Inspections are static. You don't run anything. Instead, a team gets together and systematically goes through the code or the design docs line by line, just looking for problems. It's not a replacement for testing. It's a powerful technique that works alongside it.
Now, a formal inspection isn't just a couple of people glancing over some code. No, it's a very structured process. You've got specific roles, a moderator to lead, a secretary to write everything down, and here's the really cool part. You have paraphrasers. Their job is to explain what a piece of code does in their own words. And it's amazing how often what they say doesn't match what the original author thought it did. That's how you find bugs before they're even born.
So what about really big, complex systems? Well, you handle it the same way a detective handles a massive case. You don't try to solve it all at once. Trying to test a huge system all in one go is what we call Big Bang testing, and it's a recipe for disaster, because when something inevitably breaks, good luck finding the cause. It's like looking for a needle in a giant, chaotic haystack.
A much, much better way is to do it incrementally. For example, with bottom-up testing, you start with the lowest level, most fundamental pieces of the code. But wait, how do you test them if the rest of the app isn't built yet? You use something called a test harness or a driver. It's basically a piece of code that pretends to be the rest of the system, feeding inputs to the component you're testing. This lets you make sure the foundation is solid before you build the rest of the house on top of it.
All right, we've covered a lot of ground. So, after all this detective work, what's the big takeaway? What's the bottom line on quality?
And that leads us to one last kind of challenging question. Here's a fun fact. Every time you fix a bug, there's a pretty good chance you've just created a new one somewhere else. We call it the ripple effect. So if that's true, is a truly perfect, bug-free piece of software even possible? Or is the real goal of quality something different? Maybe it's not about achieving perfection. Maybe it's about building a disciplined process to constantly find problems, manage the risks, and always be improving.